Okay, my name is Eden Kim. I'm the CEO of Calypso Systems. I'm also a member of the SNIA Solid State Storage Initiative. We chair the Solid State Storage Technical Working Group, and I'm also chair of the SNIA Technical Development Committee. One of the initiatives we've been working on in the SSSI is capturing real-world workloads. Basically, we use I/O capture tools. We grab the workloads in various deployed servers and then look at the workloads and analyze them. We've been working on this for like 5 years. Recently, it's become easier to capture these workloads and to use them to actually analyze what's going on in the server, as well as to take those server workloads and use them to test storage. So that's what this talk is about. Okay? I'm going to give you like a 3-minute what's important, and then you can download the PowerPoint and be off. If you want to hang around, I'll go through all the slides. Ask questions. I'm here for you. The slides can go in any order. I can go in any order. So just really feel free to ask questions. So basically, why are real-world storage workloads important? Well, first of all, what are they? They're the I/O streams that you capture at a certain level in the software stack, and we'll get into what that means. They're very fundamentally different from synthetic lab workloads. So when a guy makes a drive or designs firmware or a controller, he does it using corner case stress tests, which are essentially a fixed workload that's applied for some duration of a single access pattern, like let's do random 4K writes or let's do sequential 128K read-write. A real-world workload, by contrast, is comprised of a whole lot of different I/O streams that occur and keep changing with every step of the capture. So instead of seeing like a random 4K and then a sequential 128K and then a random 8K and so forth, you'll see at a given point in time tens or hundreds or thousands of discrete I/O streams. Okay, and then they change every second. So when you look at it, it's very difficult to say what my workload was unless you capture it. And when you take that constantly changing workload and apply it to storage, the storage is going to respond differently, and there's no way to tell from the published specifications how it's going to perform. Because the specs don't say, hey, if you give me 15 different I/O streams of this combination, I'm going to have this performance. Excuse me while I get back to the thing. I turned it on. Don't ever go off. So in any case, it's important to know what's in your workload in order to know how to test your storage. The other thing that's important is when you capture these I/O streams in the stack, they change from user space through every layer of software abstraction to storage. So in user space, what you think you're generating is valid, but then it goes through system cache, it goes through optimizations like dedupe compression, it goes through virtualization. So that by the time it gets to storage, it's very different than what started out in application space. Like a 4K write would likely go to cache. It may never get to the storage. It may be coalesced with other 4Ks and send a 16K block size because the storage likes 16K page sizes. So when you test your storage, knowing what your workload is at the application layer is a beginning, but it's not that accurate. You want to get as close to storage as possible. So we have these tools. They're called I/O capture tools, and you can capture the workload at various levels in the software stack and look at what your actual I/Os were when you did that work on your server. Okay, when you look at it, you can see what your performance was in real time, and you can also take that and make it into a workload and qualify storage. SNIA has put up a website, or they're actually collaborating with Calypso, who put up the website called testmyworkload.com. And at this website, there are reference I/O captures that are posted. So this is Test My Workload. I'm allowed to do this because it's a SNIA free, it's not a selfless promotion. It's a self-full promotion. If you go here, you can see these reference I/O captures that the SNIA technical working groups are using to develop the specs. So you have to start somewhere. So all captures are different, but they share certain common characteristics. So we've taken a couple sample captures and thrown them up there, and then these various technical working groups are using those to develop the test methodologies that will become standard specs. In the meantime, users can go there and see these captures, and this is the cool thing, you can download free applets that you can do a capture on your own laptop, server, desktop, whatever. For Windows, Linux, FreeBSD, Mac OS, whatever. It's very simple. You download the applet, you load it on the host side, you double click it, and it says, do you want to do a capture? You go, yes. And it says, how long do you want to do it for? You put the time in and it asks you, what resolution do you want to do? And you put 1 second or something. Then you get a capture file, and then when it's done, you can upload the capture file back to the site and see what a capture looks like. Okay? So that's the whole presentation. I'm going to go into detail, but if you have questions, yes?
What sort of overhead does the capture
So there's a default mode, and then there's like turn on all the bells and whistles. In the default mode, it's generally between 1% and 4% of CPU usage. Now, it also depends on what else you have going on in your system. If you have a really inefficient system, we've seen, high CPU usage just because there's nothing left. When you turn on advanced metrics like decompression or dedupe or, a variety of other things, it can go higher. Any other questions? So while you're at the site, if you go to demo right here, you can see there's like 6 workloads up here. I don't know if you can see it, but down the side here, example 1, 2, 3, 4, 5, 6. Example 3, 4, and 6 say SNIA SSI reference IO capture. Okay? And then if you click one of them, like number 3, which is the one we're going to talk about, so if you want to go line, you can see it because you can't see anything on the screen. When we go to number 3, it says up here, sample capture corporate portal during 24 hours. This is a corporate web portal for a 2,000 outlet retail chain. We did a 24-hour capture in 5-minute steps. So we averaged all the IO activity over every 5 minutes, and then we reported it. And then you can parse that workload and pull out things like your SQL Server IOs, and then see what the SQL Server performance was on the server when you did the capture. And then you can also take that same workload and apply it to storage. You can either replay the 24 hours in the same sequence, so you have the same demand intensity, i.e. the number of users, you'll have the same IO streams, and you'll have the same idle times. So you can see exactly how the storage would have performed had it been in that environment. And then there's all these other exotic tests you can do, which you're not really interested in, but if you are, go online, you can look at it. Okay? So that's example number 3. Example number 4 is the SNIA green storage twig. I don't know if you know what that is, but it's like the energy conservation, Energy Star, blah, blah, blah. They have a synthetic workload that's 16 different access patterns in different percentages. So we ran that and we did a capture. So basically we started a VD bench and we did the script that the SNIA green storage twig says to run. So we ran it and then we looked at, did it actually write what we thought we were generating? And it was pretty close. So you can go here and then click this tab and you'll see the stuff. So generally when you look at a workload, you see what's called an IO stream map. And this IO stream map shows you all the IOs that occur over time. So time starts on the left and goes to the right on the x-axis. So if this were a 24-hour capture, this would be midnight, and then 1 a.m. all the way to midnight. Okay. Up here, this would be your IOPS for the black line, and it also would show you the IO streams. So the IO streams are the different access patterns that occur. So if I were to see, in this case, 10 colors, that means there were 10 different IO streams that occurred. This big blue guy is like 50% of it. So 50% of the IOs were the blue guy. In this case, it's the random 4K reads, and so on and so forth. So when you see any IO stream map, all the colors just mean it's a visual representation of how many different IO streams occurred. And then it's in proportion to the size, right? So if it's, the big one is, one color, he was most of the percentage. So that's what this percentage probability is. And on the other side is the IO stream. On the right, there is a process ID box. So each of the IOs is usually tagged with a process ID. It tells you what the process associated or generated the IO. So SQL Server or system or disk check, whatever. So you can also look at the IOs by the process ID. And then there's a bunch of other stuff you can look at, but we'll get into that as we go on. If you look at the third example, this is a GPS Nav Portal. Okay, so this is a navigation website where you have GPS in your car and you upload stuff and it tells you where you are. It's back and forth. It's kind of cool. So basically it's a different looking profile. You can see that the IOPS rate is very steady, very low IOPS. There's a peak here, which is a 1 a.m. backup. Okay, you can see that there's a pretty even distribution across time, but then there's these 4 green spikes of sequential half-K writes, which are associated with some activity. So when you go on to the site, there's explanations for these things, and there's a white paper also you can download that goes into it in detail. So I'm not at all following the slides. Any more questions? Okay. So what are we going to do today? I'm going to talk about what real-world workloads are. Then we're going to talk about some of the SNIA reference IO captures, which you've already seen. We're going to pull out a SQL Server IO workload which you're going to see, and then we're going to show you how that workload played on a couple drives. Okay, those are 4 things we're going to do. So feel free to stop at any time. So when you want to analyze a storage workload, what we do is we take I/O captures, we analyze the I/O streams and the metrics from the capture, and then we can create workloads based on those I/O streams. So what are real-world storage workloads? I/O streams seen by storage that's generated in application space during your actual usage. Okay, so that's the good things, during real-world usage. So you might want to know then what's an I/O stream. An I/O stream is a discrete data transfer size. So 4K, 8K, 16K, 4.5K, 1.5K, they all come in different sizes. And they're not just even numbers like 4, 8, 16, 32. You get half K, you get 4.5K, you get 396 bytes. I mean, they come in all sizes. So a discrete transfer size, a read or write I/O, okay, and a random or sequential access. All right, so if you see a random 4K write, that is a discrete I/O stream. And if you see it occur 100 times, it's still one I/O stream. So for example here, this is a table of one step in the capture. So we take a capture for 100 steps. Each step could be 5 minutes, could be 1 second, whatever. So during this one step, we recorded all these I/Os that occurred. And the first one that's highlighted up there says sequential 1.5K writes, okay? There were 69 of them that occurred during that 1 second period, okay? But that's still one I/O stream. So if you look at all the I/O streams that occur, you would just count up the I/O streams of this table, and there's, I don't know, 18 or 20 of them, okay? The number of times they occurred in that right-hand column, you can see is the number of I/Os, and it's a really big number, all right? So I/O streams are a specific and discrete data transfer size, read-write mix, and random sequential access and queue depth that occurs during the I/O capture. Okay, what's an I/O capture? So an I/O capture is taking statistics on the I/Os that occur at some level in the stack. So we're not doing an I/O trace. We're not taking any data. We're not taking any personal data. We're not saving the actual I/Os. We're just looking at it and saying, I see a random 4K write. So you make a table. I saw the random 4K write. It occurred here. And if I'm taking other statistics, they also get captured, like LBA address, or its decompression ratio, or its dedupe ratio, or disk utilization. All kinds of things are taken with each of those discrete I/O streams, and then it's put in a table, and then it's erased. So an I/O capture is just a statistical tabulation of the metrics associated with the I/O streams at a specific level in the stack. It can be done at the file system level. It can be done at the block I/O level. It can be done for any virtual storage. Generally, when you do an I/O capture, the tool will support a specific operating system and software stack level. Okay, so if you use perfmon from Windows, that's going to be obviously Windows at the file system level. If you do Linux, you want to use block trace, that'll be at the block I/O level. Will perfmon do block I/O level? No. Okay, so if you're interested in the block I/O level, you have to find another tool. There's all kinds of tools out there you can find. There are private tools as well, and one of the private tools is Hyomon by Hyper.io, which is associated with the SNIA IOTA repository, and that's a Windows tool that's at the block level and the file system and the physical device level. And there's also the I/O capture tools at testmyworkload.com, which is Calypso, which is Windows, Linux, FreeBSD, Mac OS, and a variety of other OSs. Okay, so I already showed you testmyworkload.com. These are the I/O capture tools that are available. Also, you can download a capture applet. You can load it on your laptop, and then you can push go, and then when it's done, you can load it back up and look. So it's quiz time. You're on YouTube. You're watching your favorite video. Any rating you want, I don't care. If you do a capture of that, at the block I/O level to storage, you're going to see I/O streams. Here's the question. Will they be large block or small block? Who thinks large block? The video streaming application to storage. Large? Small? Okay. Will it be random or sequential access? Sequential? I'm trying to fool you, Random. Okay. Block size. Will it be big? Will it be small? Or in between? Okay. So typically, people think that when you see a streaming video, it's usually streaming sequentially large block reads. That's typically what you would think. But That's from the application space going through the software stack. What happens at storage is it's going to be randomized to small block read-write, 4K, 8K read-write. Why? Because the application is spooling the video from cache. So you are in application space writing large block sequential to cache and reading it, but what goes to the drive ends up being small block random read-write. And if you go to testmyworkload.com, you can look at one of the first examples, and it'll show you a Mac YouTube. Actually, you can do that. So if you go here, and you go to example number 1, it says, I think it's number 2, I'm sorry. So here's number 2, watching YouTube on a Mac, okay? And if you look at it, here is the IOStream map. You can see it was Google Chrome, Skype, and other stuff, but Google Chrome was 86% of the activity, and inside Google, obviously, was the YouTube playing. And if you look at the workload, it was random 4-byte, random 1K, random 36-byte, random 36-byte, and 1K, because this is a system-level capture. If you look at a block I/O level capture of the same thing, you can see that it's 4K read, 4K write, 4K read, 8K write, and so on and so forth. So it's really fun. It's not fun for you guys, but if you're really wonky, it's fun. You can do a capture and see what's in there, okay? If you talk to any storage professional, and I assume some of you are storage professionals, somebody might ask you, how many IOPS occur when you run your laptop and do that application? Does anybody know? A lot. Or all of them? What kind of throughput do you get? How many megabytes per second do you need? Do you know? So when you get a SSD, you go, oh, here's an SSD. It's 500 megabytes per second throughput for sequential 128K. It's got up to 100,000 4K write IOPS versus a drive that's half the price. It's 400 megabytes per second and 25,000 4K writes. Which one do you get? Well, if you can afford it, you get the one with the higher spec. But does it make a difference when you stick them into your computer and use it? Do you have any idea what the threshold is where it's meaningful? I have to have at least so many IOPS, and then at some point I got too many, I don't care. So as a storage professional, one would think that you might want to know that. But yet we're optimizing the storage stack and doing all these things without a concrete knowledge of what's going on in the stack. So if you're doing some fancy optimization like doing dedupe or doing compression or, all this stuff, do you really know what you're working with to begin with, and do you really know what's actually coming out to the storage? And on the storage side, guys will say, hey, this is all set up for an average block size of 32.5K because that's what the guys at this storage server place say they get. Do you actually know if it's 32.5K? Right? Without knowing that, then we're just kind of advancing popularized, what's the word for it? Talk story in Hawaii, that's what they say. It's just talk story. Huh? Mythology. Well, that's going a little far. I mean, people say religion, mythology, but the point is, as a professional, it seems rather intuitive. You'd really want to know what's actually going on, and I actually like to test what really goes on to the storage, and I know. Anything short of that just seems kind of weird. So the Test My Workload site is intended to get the community to do captures and upload them and get you guys to understand what's going on. Then you can ask the questions to your supplier. Hey, I saw this activity. There were, random 4K, sequential half K, and 16.5K. Does your drive support that? Okay, is there a spec that supports that? Do they even have a number? Okay, I'm wondering. Okay, so those are the I/O capture tools. Why are they important? Because they're different and they change versus being the same and constant. So everybody's workload's different, and you need to know what it is. And if you look at the software stack, it changes at each layer. So here's this picture of a Microsoft Windows stack, and the top is the user space for applications. The IOs go down through the stack, but the small block fragmented IOs can go to system cache, be coalesced, and then sent to storage, or they can be sent right back up. Things can be coalesced, they can be fragmented, they can be merged, you can have metadata appended to it. So all kinds of stuff happens. So when you see the actual I/O capture, it's very different down here at storage. Okay. So this is a list of some of the reasons why the I/O streams change. So you've got application, kernel activities, metadata, I/O appending, virtualization, cloning, You can read the slide. All right. So here's what a real world looks like. On the top frame, you can see all these up and down spikes, and each one of those columns has different colors associated with different I/O streams. So over time, you're getting a very variable combination of I/O streams that's always changing, and the demand intensity changes, the number of users. So if you look at the users that occur on the bottom, there's a green line with spikes. Okay, so sometimes you have over 300 users, sometimes you have no users, you have one user. If you take the average users across time, it's a very low number. My average queue depth is 4. Okay, great. Let's get a drive that's good at average queue depth of 4. But what happens when there's peak activity? I'm at 360. Oh, okay, well, let's do 4 to 360. I mean, you can see what I'm saying. And when you look at storage, SSDs are designed for parallelism and scalability, which means they're generally designed for a lower queue depth, and you're supposed to stack them up in parallel. But that assumes that your workload has the queue depth that's going to match that. So you want to match your queue depth, demand intensity with the operating parameters of your storage. Okay, that's it on describing it. Any questions? No questions? This is a 10-minute presentation I have to stretch to 45, so it's time to stretch. Okay, visualizing what a capture looks like. So we already went to test my workload and saw you got the IO stream map. Again, the black line is IOPS. The colors of the different data streams, and the volume or the size of the color is the percentage proportion. You can see different metrics depending on the tool. Some tools give you a lot of metrics. Some tools don't give you as much. But the important things that we want to see besides IOPS and bandwidth are average response times and maximum response times and 5 nines quality of service, if possible. Average response times don't really help a lot because it masks the response time spikes. Generally, when you have a response time spike, bad things happen. You basically get clogged up and everything behind it gets delayed. So what an I/O capture tool is good for is you can take a capture over a long period of time and you can look for I/O spikes, or I'm sorry, response time spikes. And when you see a big spike, you can zoom in there and see what activity is going on. And generally, when you have problems, it's associated with response time spikes. And you can see response time spikes that are very high, like 3,000 microseconds. I mean, 3 seconds, right? That's an eternity. You can also look at what processes are going on at the time of that spike. Okay, and you can look at different storage and match up, you know, if you're reading from one drive, writing to the other drive, and have a spike, and I'm doing an activity like replication, then you can say, okay, that's the problem area, and you can go back and address that or do whatever you want. So it's really good for failure analysis. When you look at an IO stream map, there is a little box in the lower left called cumulative workload. The cumulative workload just tells you what IO streams occurred over whatever period of time you designate. So cumulative looks at the entire capture. And what it does is it counts all the IO streams and adds them up and puts them in order of descending from most to least. And then you can display whatever number of IO streams you want based on the percent of occurrence. So we typically take a 3% clipping threshold. Any IO stream that occurs at least 3% or more of the time will show up on this map. So in this case, you can see for the SQL Server workload, there are 1, 2, 3, 4, 5, 6 IO streams that showed up at the 3% clipping threshold. And the 6 streams is 78% of all the IOs. Okay. The other thing here is there are 365 discrete IOs that occurred. All right, so we're just taking the top 6. And this shows you what the top 6 are. And if you scroll over any point, it'll highlight the specific IO stream, the percentage of occurrence, and the application associated with it. So in this case, random, I don't know, 4K writes were 23%, enable SQL Server IOs. The next one says something, and then it's something. But in any case, if you go online and look, you can see what it says. The process ID box, which is down there on the right, has only one process ID highlighted. It says SQL Server. So SQL Server is 79% roughly of all the IOs. So we click that and we said apply, and it basically rebuilds the map and shows only the SQL Server IOs. So when I took the capture, there's all this other stuff going on, but now we've filtered out everything except what we want to see. So we can see what the SQL Server IOs are and what the IOPS rate are and what the combinations are. And the 6 dominant IO streams for SQL Server are these 6 IO streams. You can also filter by event, so I can pick an event like a 2 a.m. or 1 a.m. backup. You can filter by storage, so I want to see everything on drive A or drive 1 or dev 1 or whatever you want. You can do it by time. I want to see, working hours, or I want to see my peak lunchtime hours. Okay, so what do real-world storage workloads tell us? They can show you the distribution of the I/O streams. So here you can see those 6 I/O streams by color. You can see how they occur over time. You can see response times. You can see queue depths and a whole bunch of other stuff. And now we move to the reference workloads. We saw those at testmyworkload.com, so I'm not going to spend a lot of time here. So this tells you what the 3 examples are. The example number 3 is a 24-hour retail web portal. It's a Windows Server 2012 R2. It was drive 0 and drive 1 at the block I/O level. The example 6 is a 24-hour GPS Nav Portal, which is at the file system and block I/O level. So if you go to number 6, you can compare what was at the file system, which is generally smaller block, like byte size, in terms of bytes, not like eating byte size. Anyway, byte, there's no other word, byte size transfers at the system level, and at the block I/O level, block size, which is probably why they say it's a block I/O. So why isn't file system byte I/O? Anyway. And then the green storage workload. Okay. So again, here's the I/O stream map of that 24-hour retail web portal. There's a lot of information. You can see more clearly if you go there. If you look down this list of processes, SQL Server is 79%, and then the system is 13%, and then everything else is like midgets, okay? And another thing worth noting is that even though it says 79% of the IOs are SQL Server marked, that doesn't mean those are all the SQL Server related IOs, because a lot of stuff occurs in system, and you don't see it marked as SQL Server, okay? So it's not a complete picture, but it's a good picture. And in fact, there's a lot of applications that get loaded to the system and then they run out of cache. So especially on the client side, you'll see a big spike where there's a bunch of activity and it loads to the system, and then there's nothing but system activity from then on. So there's other tools you can dive into that and try and back it out, but basically process IDs are a convenience. They're not something to rely on to be a complete representation of the application. Okay, so in this screen, we eliminated all the colored data streams, and now all you see is the black line, which is the IAPS. And then it allows you to see these workload segments that we selected. The 5 boxes below represent the cumulative workload, which is everything from left to right with all the IO streams. And then the second box is that single spike, which is a 2 a.m. backup. So if you looked at that 2 a.m. backup, it'd be 64K reads on drive 0 and 64K writes on drive 1, reading from one to the other. B is the working time, which is 8 a.m. to 5. C over here is closing evening hours. And then D is the 24-hour, but only SQL Server. So you can parse out all these different things, and based on that, you can analyze performance independently or intermixed. Further, you can then create a workload to test storage, either with everything in it, because they might say, hey, when my drive is in your server, I got to deal with everything, so let's test the drive to everything. Or on the other hand, you might say, hey, no, we really only care about the SQL Server, let's just test that. So there's a lot of things you can do with it, but at least you're testing your storage to the actual workloads that occurred. So if you want to see a comparison of what's going from drive 0 to drive 1, you can go here and click back and forth and go, ooh, cool. So if you actually look at the details, this A box is sequential 64K writes on drive 1 and 64K reads on drive 0. Okay, and then you can go ahead and compare it. Fun, fun, fun. Okay, any questions about visualization? Any questions about anything? Okay. Yes. 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 You can do it too by going online. So the replay, you don't get a streaming replay unless you buy the product, but you don't really need the replay because the static map shows you over time each step. right? I mean, we can give you the convenience of doing like a loop play, but that doesn't add any value. What's good about the site is you can zoom in on any particular point and get higher resolution visualization. And depending on the granularity that you set when you did the capture, you can see things like I/O bursts, I/O sequentiality, disk utilization, and stuff like that.
And so what tool would you use then? Is there an open source tool?
So you have to use the Calypso I/O profiler tool. Other tools don't provide all the metrics that we provide.
No, I'm talking about the generation of traffic.
Oh, so we're capturing real-world traffic, right? So you just put it on your host server of your choice, if you can get on. So in the U.S., they're all like, oh, you can't get on my server. So all of our captures are from foreign countries. Same computer, different country.
So I think the question is, you got this capture. Is there any way to turn around and have a tool generate that exact?
Yes, that's what we do. So we have a test workload. We call it the replay test. And you replay the exact combination and sequence of IOs to your storage. That's how you test your storage. So over 24 hours, you can see all these different combination of IOs and different queue depths. And we will take that, and it automatically makes a script, and then it applies those IOs to storage. So if you get the white paper that's at the Test My Workload site, it does a replay test and does it on 4 leading data center SSDs, a Samsung, a Seagate, a SanDisk, and a Micron. And it also does it to a SAS 15K HDD, a Seagate. And what's interesting is that when you look at the actual I/O performance on the server during the capture, it's very low. Why? Because it's application throttled. The application is only generating so many IOs, so it's lower, and then you got a hard disk drive JBOD. When you take that same workload and put it on a SAS HDD, it's higher because you're just applying the IOs and getting unlimited IOs. Of course, the SAS HDD is nowhere near the SSDs, right? And they're an order of magnitude or more faster. So it's really interesting to see. And on top of it, depending on what's inside that workload, because the workload had like 30% sequential half-K writes, the drive that was best at sequential half-K writes was the best overall performer. So in this case, Samsung has very good sequential half-K write performance. They'll do like 30,000 IOPS. Everybody else, Seagate does like 16,000 IOPS, and then SanDisk and Micron are down at like 1,800. Okay, so when you apply that workload for that server at that time and that application, Samsung was head and shoulders better than everybody else. But if you do another capture and those sequential half-K writes are not there, some other access pattern could dominate. So like for random AK writes, Micron is fastest. So if it was like a 90% random AK write workload, Micron would be the best drive. And so you have to know what's in there, and then you have to, see what drives are best at it. Yes?
Have you guys done any work on this as far as breaking it down to a VMware level where you've got like a VMPK to a guest and an interaction host?
Yes. Yes.
How do you differentiate?
So the tool will recognize any level of logical storage that you designate. So there's a longer answer, but we do it offline. So basically, though, the tool flexibility is great because you can pick any level of storage on the software stack and any logical storage that's recognized by the OS. The drawback is you have to get on the host to do it, and therein lies the problem. Okay, so that's a good segue into doing the test. So we extract the SQL Server I/O workload, and it's these 1, 2, 3, 4, 5, 6 I/O streams. And you can see here that the 6 I/O streams are 78% of everything that occurred, okay? And there were a total of 395 identified streams, okay? So there's 395 different I/O streams, but 78% of them were these 6. Random 64K read, sequential half-K write, which is 22%. Random 8K read, sequential 8K read, sequential 64K read, random 8K write, okay? You can look at SQL Server workloads from other captures. They're pretty close. The percentages may be a little bit different, but they generally have a similar profile. So based on similar architecture, similar software applications running, you get pretty similar I/O capture. So even though they're different and they depend, there are certain things that are common that you can look across a class of applications. We have over 400 users and over 2,000 captures now on the site. And we're in the process of aggregating similar captures for similar environments and doing a mathematical comment. I'm not doing it. Somebody smart is doing the mathematics to combine them and give a composite workload that's representative of that class of storage on that type of environment. So we hope to get to a point where we can publish reference workloads that say, hey, if you're a VMware such and such doing such and such, this is the typical workload you might see, and you can use that workload to evaluate storage and look at them in an ordinal ranking. Albeit it won't be exactly what you do, it will be a good indication of what drives would do in your environment, you know, if it's substantially similar. I sound like a lawyer. Okay. So here are the 6 IO streams. You can see that in reverse order, the random 64K reads at the bottom were 30%. The sequential half K writes were 28.9%, all the way back up. All right. So what that says is over the 24 hours, we add them all up, that's the average. But for any point in time, remember 2 a.m., right? It's 64K read write. So 64K sequential reads was 5.6%, and the sequential 64K writes don't even show up. Okay, so even though this says over the 24 hours, there is this combination of 6 IO streams, they vary from point to point to point. So when you do tests, you can do a simple test that just says, let's take the 24-hour average, these 6 cases, and for every step of the test, we're going to apply these 6 streams in this percentage, and we'll get a number. Okay, great. I get 500 megabytes per second. Well, in real life, at 2 a.m., none of this is going on. So we have another test called a replay test, which was your question, and it replays the exact sequence and order and demand intensity. Now you can see a line that goes up and down like this, and then you can pull out parts and say, okay, at 2 a.m. backup for sequential 64K read-write, all right, I had a performance of 350 megabytes versus this guy at 200. So you can start breaking it down and looking at specific things, different processes, different activities, different events. So let's get down to here. How do you read these things? They're so tiny. Okay. So there's 4 tests that we do with real-world workloads. One is a multi-write set. Multi-write set just means we're going to take all 6 of those IO streams we said, we're just going to run it all at the same time. You get one number. Okay, so for that test, you're going to get a single number. Then we can take an individual stream, which takes those 6 IO streams that we all ran together, and you run them one at a time. So you can see how the driver responds to each one of those IO streams. And the third test we can do is called a demand intensity response time histogram, which basically runs all 6, just like in the first test, but then we change the users from 1 to 1,000 and see how the performance changes depending on what the demand intensity is, right? So if you have 1 user on your server, you might have great performance. If you have 1,000 users, it might be slower. So I want to know, using that workload, what's the sweet spot? When do my response times start to go through the roof? Okay, so that's what that demand intensity response time histogram test is good for. And the last test is a replay test, which is that squiggly line in the bottom corner. So the next 4 slides zoom it up. So here's the multi-write set, all 6 streams being applied for every second of the test. So Samsung is highest performance at 17K, followed by Seagate 15, Micron 12, and then those 2 guys. Why? Because the sequential half K for Micron, which is 30% of the workload, was way faster. Okay? Then you go to the individual streams. So now we have those 6 different things. The highlighted one is the sequential half K. So with sequential half K, Micron is 32, which is twice the Seagate, which is 10 times the SanDisk, which is 15 times the Micron, which is 30 times the SAS drive. So because it is so much higher performance sequential half K, and sequential half K was such a big part of the workload, it's better. Okay, so it really pays to know what's in the workload. And the third test is that demand intensity response time histogram. So what you're seeing here is the red line is the SAS drive, hard drive. The top line is Samsung, and then Seagate, and then Micron, and then SanDisk. And basically, as you go from left to right, it's a single user and 1,000 users. So you can see as I increase the users, my performance goes up because I have to have enough demand intensity to actually see my full performance. But at some point, I saturate. And so the saturation point is where it levels off. And then if you look at the other chart, and you look at the response times, you see response times start to spike. Okay, so once I get to a certain OIO, or users of 32, when I get to 64 or 128, I don't get any more IOPS. In fact, or bandwidth, I actually go down a little bit. And if we were to look at the response times, you would see the response times start to go up. So this is good to know for a couple of reasons. It can tell you where the optimal range is for the drive. On the other hand, you don't know what your users are going to do, so you may want to know, well, how's it do across the range? Well, what's your range? Before we said the QDEP was 5 to 300. Okay, so let's look at 5 to 300 and see which drive has the best performance across all those different use cases so that we know that it's going to work no matter what, whether it's 2 a.m. with one user or 10 a.m. with 300 users. Okay? So it's a very handy test. And the replay test, this shows you the 6 different drives, the 5 drives, and the actual replay. This is the difference between the move mean. So if we were to just do it on a regular scale, there would be such a difference you wouldn't be able to see it. So here at the mean, you can see that some drives are 15,000 above the mean and some are 15,000 below the mean. Basically, the reference is the self-test, which is the red line, and the SAS hard drive down here. Then you got SanDisk. You got Micron kind of in the middle, and you got Seagate and Samsung at the top. If you look over time, you can kind of see what events occurred. So you can go back, and I know that basically the 1 a.m. backup is here. I know this is low intensity time. I know this is users. I know this is closing time. But again, for the storage test, we're running full blast. Okay, we're not throttling to match what occurred. We're saying, I'm going to let you generate as many IOs as you can, given the demand setting of queue depth or whatever. So we change the queue depth to every IO command, but we don't limit the number of IOs the drive can do. So given 32 users, how many IOs can you do? And this SSD will give you 15,000. All right, but in the actual server, it's IO throttled. There's only so many application IOs going to storage, so you only get a number of 30. Okay? So if you go to test my workload and click, you'll see this black box. You can click that, you put your name and email in, you can get the white paper, and the white paper gives you all the data and all the charts on these different drives. And what's interesting is that if you were to use the published specs from the manufacturer or you use the SNIA test, these drives are kind of similar. But when you use the real-world workload test, there's a big separation. So it pays to know what's going on, and it pays to know which drives respond better to it. Hi, Greg. Any questions? No questions? What's the name of the website you go to get the free capture tools? Yes. If I do a video to storage, large block or small block? Read or write? So next time you meet your guru in your company, like a smart guy with storage, just ask him, hey, when we're at peak traffic, how many IOs are going to storage? And then when he kicks you out of the office, email him a link to testmyworkload.com. So we definitely are looking for collaboration in the industry. So if you have an ability to do captures, we'd love to get them. You can do them on your own. It's free. If you upload a capture to Test My Workload, the thing at the bottom you don't ever click says that you agree that by uploading it, we can look at them and we can actually use the data to show it as long as it's anonymized. Okay? The more captures we get, the better baseline we have, and we can provide more stuff. There's a free version that lets you capture and look at it, and then there's pay more, pay a lot for different things. Paying a lot's really cool if you want to test storage, but the pay some gives you a tool that lets you have everything on your own database, because a lot of people are firewalled out, they can't actually go there. So you can get a pretty low-cost version that allows you to have all the stuff at your corporate server inside your firewall and nobody else sees it. And I guess that's kind of important to a lot of people. So that's pay for a little bit. Pay for a lot of it is we can give you hardware and a tester, and you can plug the drives in, and you can do all kinds of fancy testing that's all automated. So that was a shameless self-promotion. That's at testmyworkload.com or calypsotesters.com. Okay? Thank you for your time. Ask me questions anytime. The next guy up is David. Oh, he's here. Oh. And he's a great keyboard musician. He can rip. And if you're nice, he might do something with his laptop. All right, that's it. Thank you very much.